This is Colin Selleck of Binghamton University. This lecture is on potential energy and conservation of energy. It's from chapter 14.5 to 14.6 of the book Dynamics by R.C. Hibbeler. Today's objectives: you will be able to understand and use the concept of conservative forces and determine the potential energy of such forces. You will also be able to apply the principle of the conservation of energy. Activities include some applications, the conservative force, the potential energy, conservation of energy, and some problem solving. So here's an application. The weight of these sacks compresses these springs and stores potential energy in them. As you remove these sacks, the platform will slightly rise, since some of the potential energy in the springs will be transformed into an increase in gravitational potential energy of the sacks. If the sacks weigh 100 pounds, and the spring constant is 500 pounds per foot, what is the energy stored in the springs? Here, a young woman is launching a water balloon. She pulls back on the balloon, stretching 4 elastic cords. If we know the unstretched length and stiffness of each cord, can we determine the maximum height and range of the water balloon? Here's a roller coaster. Let's say this car at A is released from rest. Can you determine the velocity at points B and C? Can you determine the minimum height h required so that the cars travel around loops B and C without leaving the track? So let's talk about the conservative force. This is section 14.5. A force F is said to be conservative if the work done is independent of the path followed by the force. So this force F travels along this path from A to B. The work done is independent of the path traveled. In addition, if the force travels from A to B back to A again, the total work done is 0. So remember, the equation for work is F dot dr. So as it travels from A to B and back to A, the work done is 0. Thus, we say the work is conserved. Note that the work done by conservative force depends only on the position of the particle and is independent of the velocity and acceleration. The conservative potential energy of a system is typically written using the potential function V. So V stands for potential energy. Use the uppercase V to distinguish it from velocity, which is a lowercase v. In this course, the potential energy comes mainly from 2 places. The first one is the potential energy due to gravity, and the other one is the potential energy due to a spring. And the total potential energy is just, the sum of these 2. So let's discuss the potential energy due to gravity and spring in more detail. So first we'll discuss the potential energy due to gravity. The potential function for a gravitational force is the weight times the elevation from a datum. So if you have this weight and you lift it to a new location that is plus y above the datum, and remember, this is independent of the path taken. I could have done this, and the potential energy would have still been the same thing. So potential energy in this situation is the weight times the change in the elevation. And if you're raising the weight, the potential energy is positive. If you lower the weight, the potential energy is negative. Obviously, this particle has more potential energy than this particle since it's at a higher level. So the other type of potential energy is elastic. Here we have a spring in the unstretched position, and obviously the elastic potential energy is 0 at that point. As you extend the spring a distance s from the unstretched position, that's very important, the potential energy is defined as 1/2 ks squared. If you compress the spring minus s, again the potential energy is 1/2 ks squared. Notice that these are both positive. The s term is squared, so it's always positive. It's also very important that s be measured from the unstretched position. So when a particle is acted upon by a system of conservative forces, the work done is conserved and the sum of kinetic and potential energy remains constant. So in other words, we have the kinetic energy at point 1 plus the potential energy at point 1. That has to equal the kinetic energy at point 2 plus the potential energy at point 2. Remember, the kinetic energy is 1/2 the mass times the velocity squared. So this principle is called the conservation of energy. The energy in state 1 is equal to the energy in state 2. So let's do some examples. Here we have a 4 kilogram collar at C. It has a velocity of 2 meters per second at point A. The spring constant is 400 newtons per meter, and the unstretched length of the spring is 0.2 meters. Find the velocity of the collar at point B. Our plan is to apply the conservation of energy principle between points A and B. So I'll set my datum here level with point A, and my equation is going to be the kinetic energy at point A plus the potential energy at point A is the kinetic energy at point B plus the potential energy at point B. So let's do these one by one. The kinetic energy at point A is 1/2 mv squared. So 1/2 times the mass, which is 4, and we were given that the velocity at point A is 2 squared, is 2. So this comes out to be 8 Newton meters. Now the potential energy at A is only due to the potential energy of the spring, since A is level with our datum. So that would be 1/2 times K, which is 400 newtons per meter, times S sub A squared. Now S sub A is going to be the amount that the spring is compressed or extended at point A. So at point A you can see that the spring length is 0.1 meters. We were told the unstretched length was 0.2 meters, so the spring is compressed by 0.1 meters at that point A. So this equals 2 Newton meters. So the kinetic energy at point B is 1/2 the mass, which is 4, times the velocity at B. That's what we're looking for. So this is equal to 2 the velocity at B squared. Now the potential energy at point B is due to two things. It's due to the change in elevation of the collar, and it's due to the potential energy in the spring. So the potential energy due to gravity is the weight, which is 4 kilograms times 9.81, times the change in elevation, which is 0.3 plus 0.1. Now it's going down, so that is negative, so that's minus 0.4. And we'll add to that the potential energy due to the spring, which is 1/2 times K, 400 newtons per meter, times S sub B squared. S sub B is going to be the amount the spring is extended from the unstretched length at point B. We can see the spring length is 0.5 meters at point B. The unstretched length is 0.2 meters. So we want 0.5 minus 0.2, or 0.3 squared. So this reduces to 2.3 Newton meters. So now we can go back to our equation here and substitute in the terms. TA is 8 newtons per meter. V sub A is 2 Newton meters. That equals to TB, which is 2 VB squared, plus VB, which is 2.3. And you can solve for the velocity at B and get 1.96 meters per second. Here's another problem. We have an 800 kilogram roller coaster car. It's released from rest at point A. We want to find the minimum height h of point A so that the car travels around this inside loop B without leaving the track. We also want to find the velocity of the car at point C. So our plan is to determine the velocity at B using the equations of motion, and then apply the conservation of energy equation to find the minimum height h. So my conservation of energy equation would be kinetic energy at A plus potential energy at A is equal to kinetic energy at B plus potential energy at B. So we'll do these in order. The kinetic energy at A is 1/2 mv squared, so 1/2 times the mass, which is 800, times the velocity at A squared, which is 0. And likewise, the potential energy at A is mg times delta H above the datum, but that's also 0. So potential energy at A is also 0. Now the kinetic energy at B is 1/2 the mass, 800 kilograms, times the velocity at B squared. And that's what we're looking for, velocity at B. The potential energy at B is the mass times gravity times the difference in height between A and B, which is going to be h minus 20. You have to be careful though, because this is going to be negative potential energy since it's below the datum, so we'll put a minus sign there. So now we can go back to this equation here. Kinetic energy at A plus potential energy at A is equal to 1/2 800 velocity at B squared minus 800 times 9.81 times h minus 20. So now I have one equation and two unknowns, so we need to go to kinematics to get another equation. So to do that, let's find the velocity at B so that it doesn't leave the track. Let's draw a free body diagram. So we have the weight, mg, and the normal force from the track. Now it's important to note here that the normal force is going to be 0. We're looking for the minimum height required, so as the car moves around the track, it's just going to reach the top where the normal force is 0, and then it's going to drop again. So I'll call this the normal direction, and we'll sum forces in the normal direction and set it equal to the mass times acceleration in normal direction at B. So since the normal force is 0, the only force in the normal direction is the mass times g. That equals to the mass, which is 800, times acceleration at B in the normal direction, which will be the velocity at B squared divided by rho, which is 7.5. Now we can use this to solve for the velocity at B, 8.578 meters per second. Now we know the velocity at B. We can substitute it into this equation here and solve for h. And h comes out to be 23.75 meters. So I just wanted to add a note about why the normal force at point B is 0. We were asked to give the minimum height h to ensure that the car won't leave the track at B. So let's imagine that h is a very large number, and the velocity at B is very, very high. That track has to keep that car on the track, so there's going to be huge normal forces along the way to do that. Decrease the velocity by half. You can see, the normal forces are going down. Decrease it again, eventually the normal force at the peak is going to reach 0. So if you drop the height and therefore the velocity at B anymore, the car can't quite make it. It's going to leave the track, right? It's going to come up and do this. So we're looking for the free body diagram to be mg, and this normal force is equal to 0. So then you sum the forces in the normal direction, and it's mg is equal to m, velocity at B squared over rho. The m's cancel, we know rho, we can solve for velocity at B. Now we were also asked for the velocity at C, so we'll use the conservation of energy equation there. So potential plus kinetic energy at A is equal to kinetic energy at C plus potential energy at C. We already know these are both 0. The kinetic energy at point C is going to be 1/2 the mass, which is 800, times the velocity at C squared. That's what we're looking for. Plus the potential energy at C, which is going to be mg delta h, so it's 800 times g, 9.81, times delta h, which we calculated previously to be 23.75, but c is below the datum, so that's negative. So we'll put minus 23.75. And you can solve this for the velocity at c, 21.6 meters per second. This concludes section 14.5 to 14.6, potential energy and conservation of energy. Next up is chapter 15, impulse and momentum.